Ok. Hôm nay thì mình sẽ coi lại gradient descent và các kiến thức machine learning.
Minus the step size. So we plug in the numbers, intercept, and get the sum of the squared residuals. Thus, we now have an equation for this curve, and we can take the derivative. Is the difference between the observed height, which is 1.9, and the predicted height, which comes from the equation for the line. And since this individual weighs 2.3, we do them step by step. This stat quest assumes you already understand the basics of least squares and linear regression, so if you're not already down with that, check out the quest. In statistics, machine learning, and other data science fields, we optimize a lot of stuff.
The sun is out and it's nice outside. It's the perfect weather for StatQuest. Yeah. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about backpropagation details, part 1. Note, this StatQuest assumes that you have already watched Neural Networks Part 2, Backpropagation Main Ideas. If not, check out the quest. The link is in the description below. In Backpropagation Main Ideas, we had this super simple dataset that showed whether or not different drug dosages were effective against a virus. Then we had this simple neural network that already had optimal values for all of the parameters, except for the last bias term, b sub 3. Then, using everything in the neural network except for the last bias, b sub 3, we drew this green squiggle. Then we demonstrated the main ideas behind backpropagation by optimizing b sub 3. We first used the chain rule to calculate the derivative of the sum of the squared residuals with respect to the unknown parameter, which in this case was b sub 3. To calculate the derivative of the sum of the squared residuals with respect to the unknown parameter, which in this case was b sub 3. Then we initialized the unknown parameter with a number, and in this case we set b sub 3 equal to 0, and used gradient descent to optimize the unknown parameter. Hooray! We can optimize the last bias term, b sub 3. Now let's pretend we don't know b sub 3's optimal value, and start working our way backwards so that, along with b sub 3, we optimize the last two weights, w sub 3 and w sub 4. Note, the goal of this quest is to learn how the chain rule and gradient descent applies to multiple parameters and introduce some fancy notation. In the next part, we'll go completely bonkers with the chain rule and learn how to optimize all 7 parameters in this neural network simultaneously. Bam! So let's go back to not knowing the optimal values for w sub 3, w sub 4, and b sub 3, and, just like before, we'll assume that the other weights and biases are already optimized. The first thing we do is initialize the weights, w sub 3 and w sub 4, with random starting values. And, in this example, that means we randomly select 2 values from a standard normal distribution. Then we initialize the last bias, b sub 3, to 0, because bias terms frequently start at 0. Now, if we run dosages from 0 to 1 through the connection to the top node in the hidden layer, then, just like before, we get the corresponding y-axis coordinates and this blue curve. Now we multiply the y-axis coordinates on the blue curve by w sub 3, which starts out with the random value 0.36, and we get this new blue curve. Now, if we run dosages from 0 to 1 through the connection to the bottom node in the hidden layer, then, just like before, we get the corresponding y-axis coordinates for this orange curve. Now we multiply the y-axis coordinates on the orange curve by w sub 4, which starts with a random value 0.63, and we get this new orange curve. Now we add the blue and orange curves together and get this green squiggle. Lastly, since the initial value for b sub 3 is 0, adding it to the y-axis values on the green squiggle does not change anything. In other words, given the current parameters for this neural network, some of which are optimal and some of which are not optimal, we end up with this green squiggle. Now, just like before, we can quantify how well the green squiggle fits the data by calculating the sum of the squared residuals. And we get the sum of the squared residuals equals 1.4. Now, even though we have not yet optimized w sub 3 and w sub 4, we can still plot the sum of the squared residuals with respect to b sub 3. And just like before, if we change b sub 3, then we will change the sum of the squared residuals. And that means, just like before, we can optimize b sub 3 by finding the derivative of the sum of the squared residuals with respect to b sub 3 and plugging the derivative into the gradient descent algorithm to find the optimal value for b sub 3. And, just like before, because the predicted values in the sum of the squared residuals come from the green squiggle, and the green squiggle is the sum of the blue and orange curves plus b sub 3, then the sum of the squared residuals are linked to b sub 3 by the predicted values. So, by the chain rule, the derivative of the sum of the squared residuals with respect to b sub 3 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to b sub 3. Note, this is the exact same derivative that we calculated in backpropagation main ideas. The point of this is that even though we are now optimizing more than one parameter, the derivatives that we have already calculated with respect to the sum of the squared residuals do not change. Bam! Now let's talk about how to calculate the derivatives of the sum of the squared residuals with respect to the weights w sub 3 and w sub 4. Unfortunately, before we can do that, we have to introduce some fancy notation. First, let's remember that the I in this summation notation is an index for the data in the dataset. For example, when I equals 1, we are talking about observed sub 1, which is 0. And we are talking about predicted sub 1, which is 0.72. However, we can also talk about dosage sub I. And when I equals 1, we are talking about dosage sub 1, which is 0. When I equals 2, we're talking about dosage sub 2, which is 0.5. And when I equals 3, we are talking about dosage sub 3, which is 1. And because dosage sub I is the input value, we call it input sub I. And that means this connection multiplies input sub I by weight w sub 1, which is 3.34. And it adds bias sub 1. Which is negative 1.43, to get an x-axis coordinate for the activation function in the top node in the hidden layer. Meanwhile, the other connection multiplies input sub I by weight w sub 2, which is negative 3.53, and adds bias b sub 2, which is 0.57, to get an x-axis coordinate for the activation function in the bottom node in the hidden layer. So we have two different x-axis coordinates for input sub I. In order to keep track of things, let's call this x-axis coordinate x sub 1 comma I, where the 1 in 1 comma I refers to the activation function in the top node. And the I in 1, I tells us that it corresponds to input sub I. Likewise, let's call this x-axis coordinate x sub 2, I, where the 2 in 2, I refers to the activation function in the bottom node, and the I in 2, I tells us that it corresponds to input sub I. For example, if I equals 3, then we're talking about the third dosage sub 3. And that means we're talking about input sub 3, which is 1, maximum dosage. And that means the x-axis coordinate for the activation function in the top node, x sub 1, 3, is equal to 1.91. And the x-axis coordinate for the activation function in the bottom node, x sub 2, 3, is equal to negative 2.96. Bam. If we plugged in all values for I into dosage sub I, we get x sub 1, I values in this red box, and x sub 2, I values in this red box. Now, in order to get the y-axis coordinates for the activation function in the top node, we plug x sub 1, I into the activation function, which, in this example, is the soft plus function, and that gives us y sub 1, I. Just like before, the 1 in 1, I tells us that we are talking about the activation function in the top node, and the I tells us which dosage we are talking about. Likewise, in order to get the y-axis coordinates for the activation function in the bottom node, we plug x sub 2, I into the activation function, and that gives us y sub 2, I. Bam! Now that we understand the fancy notation, we can talk about how to calculate the derivatives of the sum of the squared residuals with respect to the weights w sub 3 and w sub 4. First, remember that y sub 1, I represents the y-axis coordinates for the top activation function, and they form this initial blue curve. However, we get the final blue curve by multiplying the y-axis coordinates y sub 1, I by w sub 3. And that means we can plug y sub 1, I times w sub 3 into the equation for the predicted values. Likewise, w sub 4 multiplies the y-axis coordinates y sub 2, I from the bottom activation function to create the final orange curve. And that means we can plug y sub 2, I times w sub 4 into the equation for the predicted values. Now, since this sum creates the green squiggle, and the green squiggle gives us predictions that we evaluate with the sum of the squared residuals, then the sum of the squared residuals are linked to w sub 3 and w sub 4 by the predicted values. That means we can use the chain rule to determine the derivative of the sum of the squared residuals with respect to w sub 3 and with respect to w sub 4. The chain rule says that the derivative of the sum of the squared residuals with respect to w sub 3 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to w sub 3. Likewise, the derivative with respect to w sub 4 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to w sub 4. Double bam? Not yet. Note, in both cases, the derivative of the sum of the squared residuals with respect to the predicted values is the exact same as the derivative used for b sub 3. Just to remind you, we start by substituting the sum of the squared residuals with its equation. Then we use the chain rule to move the square to the front, and then we multiply that by the derivative of the stuff inside the parentheses with respect to the predicted values, -1. Lastly, we simplify by multiplying 2 by -1. And this is the derivative of the sum of the squared residuals with respect to the predicted values. So we just plug it in. Now, to solve for the derivative of the predicted values with respect to w sub 3, we plug in the equation for the predicted values, and the derivative of the first term with respect to w sub 3 is y sub 1, I. And the derivatives of the other terms are both 0 since they do not contain w sub 3. And we end up with just y sub 1, I. So we multiply the derivative of the sum of the squared residuals with respect to the predicted values by y sub 1, I. Likewise, the derivative of the predicted values with respect to w sub 4 is 0 for the first term, plus y sub 2, I for the second term, plus 0 for the third term, which is just y sub 2, I. So we multiply the derivative of the sum of the squared residuals with respect to the predicted values by y sub 2, I. Double bam! Now that we have the derivatives of the sum of the squared residuals with respect to w sub 3, w sub 4, and b sub 3, we can plug them into gradient descent to optimize w sub 3, w sub 4, and b sub 3. First, we initialize w sub 3 and w sub 4 with random values and set b sub 3 equal to 0. Now, starting with the derivative of the sum of the squared residuals with respect to w sub 3, first, we expand the summation. Then we plug in the observed values, and plug in the predicted values from the green squiggle. Remember, we get the predicted values on the green squiggle by running the dosages through the neural network. Now we plug in the y-axis coordinates for the activation function in the top node, y sub 1, I. Lastly, we do the math and get 2.58. Likewise, we calculate the derivative of the sum of the squared residuals with respect to w sub 4 and with respect to b sub 3. Now we use the derivatives to calculate the new values for w sub 3, w sub 4, and b sub 3. Now we repeat that process until the predictions no longer improve very much, or we reach a maximum number of steps, or we meet some other criteria. Now let's check out a fancy animation that shows the gradient descent in action. These gray dots represent the data that we are using to train the neural network, and the orange and blue curves represent the orange and blue curves. And the green squiggle represents the sum of the orange and blue curves plus b sub 3. Now, watch how the green squiggle fits the data after 175 steps in gradient descent. Bam! So, after a bunch of steps, we see how gradient descent optimizes the parameters. Triple bam! In the next StatQuest, we'll go totally bonkers with the chain rule and show how to optimize all of the parameters in a neural network simultaneously. Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out the StatQuest study guides at statquest.org. There's something for everyone. Hooray! OMG, let's do the chain rule with me. It's gonna be cool, you'll see. StatQuest. Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to talk about backpropagation details, part 2. Note, this StatQuest assumes that you have already seen backpropagation details part 1. If not, check out the quest. The link is in the description below. Since you've already seen backpropagation details part 1, you already know that in this StatQuest we're going to go totally bonkers with the chain rule and gradient descent in order to optimize all of the weights and biases in this neural network so that it can fit a green squiggle to this data. Bam! Note, the derivatives that we derived in part 1 for bias b sub 3 and weights w sub 3 and w sub 4 do not change. So we can just plug these derivatives into the gradient descent algorithm. However, now we need to derive the derivatives of the sum of the squared residuals with respect to w sub 1, b sub 1, w sub 2, and b sub 2. Let's start with the derivative of the sum of the squared residuals with respect to w sub 1. Remember, the neural network starts by multiplying input sub I by w sub 1. Then it adds the bias b sub 1, and that gives us an x-axis coordinate for the activation function that we call x sub 1 comma I. We then plug x sub 1 comma I into the activation function, and that means plugging x sub 1 comma I into this equation because we are using the soft plus activation function. And that gives us a y-axis value of y sub 1 comma I. And remember, y sub 1 comma I times w sub 3 gives us the final blue curve, which we add to the final orange curve, and the bias b sub 3, to get the green squiggle and the predicted values. Lastly, remember that we use the predicted values to calculate the sum of the squared residuals. Now, let's clear the screen and spread out the equations. Now we can see that the sum of the squared residuals are linked to w sub 1, first by the predicted values, then y sub 1 comma I, the y-axis values that come from the activation function. And lastly, x sub 1 comma I, the x-axis values that are input for the activation function. Thus, the chain rule tells us that the derivative of the sum of the squared residuals with respect to w sub 1 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to y sub 1 times the derivative of y sub 1 with respect to x sub 1 times the derivative of x sub 1 with respect to w sub 1. As we've seen before, the derivative of the sum of the squared residuals with respect to the predicted values is the sum of -2 times the observed minus the predicted values. Now the derivative of the predicted values with respect to y sub 1 is w sub 3 for the first term and 0 for the other two terms. So the derivative of the predicted values with respect to y sub 1 is w sub 3. Now we need to solve for the derivative of y sub 1 with respect to x sub 1. This requires knowing that the derivative of the log of z is 1 divided by z, and the derivative of e to the x is e to the x. The chain rule tells us to take the derivative of the stuff outside the first term and 0 by the predicted values, then y sub 1 comma I, the y-axis values that predicted values. Lastly, remember that we use the predicted values to calculate the sum of the squared residuals. Now, let's clear the screen and spread out the equations. Now we can see that the sum of the squared residuals are linked to w sub 1, first by the predicted values, then y sub 1 comma I, the y-axis values that come from the activation function. And lastly, x sub 1 comma I, the x-axis values that are input for the activation function. Thus, the chain rule tells us that the derivative of the sum of the squared residuals with respect to w sub 1 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to y sub 1 times the derivative of y sub 1 with respect to x sub 1 times the derivative of x sub 1 with respect to w sub 1. As we've seen before, the derivative of the sum of the squared residuals with respect to the predicted values is the sum of -2 times the observed minus the predicted values. Now the derivative of the predicted values with respect to y sub 1 is w sub 3 for the first term and 0 for the other two terms. So the derivative of the predicted values with respect to y sub 1 is w sub 3. Now we need to solve for the derivative of y sub 1 with respect to x sub 1. This requires knowing that the derivative of the log of z is 1 divided by z, and the derivative of e to the x is e to the x. The chain rule tells us to take the derivative of the stuff outside of the parentheses, the log function, times the derivative of the stuff inside the parentheses, 1 plus e to the x. If we let z equal 1 plus e to the x, then the derivative of the stuff outside is 1 divided by 1 plus e to the x. And the derivative of the stuff inside is 0 for the first term, since it does not include x, plus e to the x for the second term. And this whole thing simplifies to e to the x divided by 1 plus e to the x. Lastly, the derivative of x sub 1 with respect to w sub 1 is the input value for the first term plus 0 for the second term, because it does not include w sub 1, which simplifies to just the input values. Plugging in the derivatives gives us a big fancy equation, or BFE for short. Hooray! We solved for the derivative of the sum of the squared residuals with respect to the first weight, w sub 1. Note, keep in mind that the x's in the e to the x terms are the individual x-axis coordinates for the activation function for each input value. Bam! Now let's find the derivative of the sum of the squared residuals with respect to b sub 1. The good news is that the exact same equations that linked the sum of the squared residuals to w sub 1 also link the sum of the squared residuals to b sub 1. Thus, the chain rule tells us that the derivative of the sum of the squared residuals with respect to b sub 1 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to y sub 1 times the derivative of y sub 1 with respect to x sub 1 times the derivative of x sub 1 with respect to b sub 1. And the derivative of the sum of the squared residuals with respect to the predicted values is the same as before. And so is the derivative of the predicted values with respect to y sub 1. And the derivative of y sub 1 with respect to x sub 1 is also the same as before. And the only thing different is the derivative of x sub 1 with respect to b sub 1, which is 0 for the first term, since it does not include b sub 1, plus 1 for the second term, which simplifies to just 1. Plugging in the derivatives gives us another big fancy equation. Double bam! We've solved for the derivatives of the sum of the squared residuals with respect to w sub 1 and b sub 1. Now we need to solve for the derivatives of the sum of the squared residuals with respect to w sub 2 and b sub 2. The good news is that the only difference is that instead of using the top node in the hidden layer, we use the bottom node. And that means now we multiply input sub I by w sub 2 and add b sub 2. And that gives us x sub 2 comma I, which we plug into the activation function to get y sub 2 comma I. Then we multiply y sub 2 comma I by w sub 4 to get the final orange curve, which we add to the final blue curve, and b sub 3 to get the green squiggle. And the green squiggle gives us the predicted values, which gives us the residuals and the sum of the squared residuals. Thus, just like before, the sum of the squared residuals are linked to w sub 2, and we use the chain rule to derive the derivative of the sum of the squared residuals with respect to w sub 2. Now, calculating the derivatives is just like before, but with slightly different parameter names. And plugging in the derivatives gives us another BFE. So, in total, this is the derivative of the sum of the squared residuals with respect to w sub 2. Similarly, we can derive the derivative of the sum of the squared residuals with respect to b sub 2. Now we just combine these derivatives with all of the others, and use gradient descent to optimize all of the parameters simultaneously. First, we initialize the weights and biases. In this example, we pick numbers from a standard normal distribution for the weights. Oh no, it's a technical detail alert. I think this is the first time that's ever happened. Just so you know, using a standard normal distribution is just one of many ways to initialize weights. Small bam. Now we initialize the bias terms to 0, because bias terms frequently start at 0. Now, starting with the derivative of the sum of the squared residuals with respect to w sub 1, we expand the summation. Then we plug in the observed values, and the values predicted by the green squiggle. Remember, we get the predicted values on the green squiggle by running the dosages through the neural network. Now we can plug in the current value for w sub 3, and the x-axis coordinates for the activation function in the top node, x sub 1 comma I. Lastly, we plug in the input values. We do the math, and get 0.76. Then we solve for all of the other derivatives. And then we use each derivative to calculate a step size and a new value. Then we update the parameters in the neural network, and repeat until the predictions no longer improve very much or we meet some other criteria. Now let's check out a fancy animation that shows the gradient descent in action. These gray dots represent the data that we are using to train the neural network, and the orange and blue curves represent the orange and blue curves. And the green squiggle, which fits the data so poorly that it's going off the screen, represents the sum of the orange and blue curves plus b sub 3. Now, watch how gradient descent fits the green squiggle to the data after 450 steps. Bam! We went totally bonkers with the chain rule and gradient descent. And we finally have a neural network that fits a green squiggle to the data. Triple bam! Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out the StatQuest study guides at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to Else Part 1. If not, B sub 1, W. Some people say I mispronounce revenue, but that is okay. At least it's okay with me. StatQuest. Hello, I'm Josh Darmer. Welcome to StatQuest. Today we're going to do Neural Networks Part 3, the ReLU activation function in action. Note, this StatQuest assumes that you are already familiar with the main ideas behind neural networks. If not, check out the quest. The link is in the description below. In Neural Networks Part 1, inside the black box, we started with a simple dataset that showed whether or not different drug dosages were effective against a virus. The low and high dosages were not effective, but the medium dosage was effective. Then we talked about how a neural network like this one, that uses the soft plus activation function in the hidden layer, can fit a green squiggle to the dataset. Bam. Now let's see what happens if we swap out the soft plus activation function in the hidden layer with one of the most popular activation functions for deep learning in convolutional neural networks, the ReLU activation function, which is short for rectified linear unit and sounds like a robot.
Linear unit.
And, as a bonus, because it is common to put an activation function before the final output, we'll do that too. Bam! Bonus, because it is common to put an activation function before the final output, we'll do that too. Bam! Remember, to keep the math simple, let's assume dosages go from 0 for low to 1 for high. So if we plug in the lowest dosage, 0, the connection from the input to the top node in the hidden layer multiplies the dosage by 1.70 and then adds negative 0.85. And the result is an x-axis coordinate for the activation function. So if we plug in 0 for dosage, then the x-axis coordinate for the activation function is negative 0.85. Now we plug negative 0.85 into the ReLU activation function. The ReLU activation function outputs whichever value is larger, 0 or the input value, which in this case is negative 0.85. And because 0 is greater than negative 0.85, the output from the ReLU activation function is 0. And the corresponding y-axis value is 0. So let's put a blue dot at 0 for when dosage equals 0. Now, if we increase dosage to 0.2, the x-axis coordinate for the activation function is negative 0.51. And again, because 0 is greater than negative 0.51, the output from the ReLU activation function is 0. And the corresponding y-axis value is 0. So let's put a blue dot at 0 for when dosage equals 0.2. And if we increase the dosage value to 0.4, we get 0 for the y-axis coordinate. Again. However, when dosage equals 0.6, the x-axis coordinate is 0.17. Now, when we plug 0.17 into the ReLU activation function, the output is 0.17 because 0.17 is greater than 0. And the corresponding y-axis value is 0.17. And if we continue to increase the dosage values all the way to 1, the maximum dosage, we get this bent blue line. Then we multiply the y-axis coordinates on the bent blue line by negative 40.8, and the new bent blue line goes off the screen. Wah wah. Note, for those of you drawing this at home, your final bent blue line will have a steeper slope than mine because, for the sake of clarity, I am not drawing things perfectly to scale. Tiny bam. Now when we run dosages through the connection to the bottom node in the hidden layer, we get the corresponding y-axis coordinates that go off the screen for this straight orange line. Now we multiply the y-axis coordinates on the straight orange line by 2.70. And we end up with this final straight orange line. Now we add the bent blue line and the straight orange line together to get this green wedge. Now we add the final bias term, negative 16, to the y-axis coordinates on the green wedge. Lastly, because we included the ReLU activation function right in front of the output, we use the green wedge as its input. For example, the y-axis coordinate for this point on the green wedge is negative 16, which corresponds to this x-axis coordinate for the ReLU activation function. And when we plug that into the ReLU activation function, we get 0, because 0 is greater than negative 16. And 0 corresponds to this green dot. Likewise, the y-axis coordinate for this point on the green wedge is negative 9.2. And just like before, when we plug that into the ReLU activation function, we get 0. And 0 corresponds to this green dot. Now, in contrast to the last 2 points we fed into the ReLU activation function, this one is positive, 0.49. And when we plug it into the ReLU activation function, we get 0.49. and 0.49 corresponds to this green dot. Likewise, the remaining positive y-axis coordinates stay the same, and the negative values are set to 0. And at long last, we end up with this green pointy thing. Double bam! Thus, the ReLU activation function may seem weird because it's not curvy, and the equation is really simple. But just like for any other activation function, the weights and biases on the connections slice them, flip them, and stretch them into new shapes, which are added together to get an entirely new shape that fits the data. Triple bam! Oh no, it's another technical detail alert. Some of you may have noticed that the ReLU activation function is bent and not curved. This means that the derivative is not defined where the function is bent. Because gradient descent, which we use to estimate the weights and biases, requires a derivative for all points. However, it's not a big problem, because we can get around this by simply defining the derivative at the bent part to be 0 or 1. It doesn't really matter. Small bam. And now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out the StatQuest study guides at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting stat.
Don't be afraid of neural networks, they're not scary. Even when a neural net says boo. Hello, I'm Josh Starmer, host of the StatQuest with Josh Starmer YouTube channel, and I'm here to say that
way up north, there's an island out in the sea. And way out there, they've got neural networks and they're cool. StatQuest. Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to talk about neural networks part 4, multiple inputs and outputs. Note, this StatQuest was supported in part by Ital. Also, I thought I'd mention that the inspiration for this StatQuest came from my friend Michael in Svalbard. Lastly, this StatQuest assumes that you already understand the main ideas behind neural networks and the ReLU activation function. If not, check out the quests. The links are in the description below. So far, the neural networks that we've looked at have been super simple and only predict whether or not the dosage of a drug will be effective. The neural networks just have one input node and one output node. When there is only one input node, then the data we are using to make predictions, in this case, dosages, can all fit on the x-axis of this graph. In other words, the input is one-dimensional, since it only needs one axis in the graph. Likewise, a single dimension, the y-axis, represents the output values. Combined, we get a two-dimensional graph with the input, dosage, on the x-axis and the output, drug effectiveness, on the y-axis. Because the input and output combine to form a two-dimensional graph, we can see how the weights and biases in this neural network slice, flip, and stretch the curved or bent activation functions into new shapes that are added together to make a two-dimensional squiggle or shape that fits the data. Pip, 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 pip. Bam. Now let's look at a more complicated network that has more than one input node and more than one output node. Now, this neural network may look really fancy, but all it does is take two measurements from an iris flower, the width of a petal, which is this part of the flower, and the width of a sepal, which is this part of the flower. And with that information, it predicts the species, either Setosa, versicolor, or virginica. Now, raise your hand if you already knew that this was a sepal and not a petal. Not me. I thought they were all petals. Anyway, to keep things simple at the start, let's begin with both input nodes, but just one output node for Setosa. Later on, we'll add the other two output nodes, but for now, let's keep things simple and just use one output node. Now let's see what happens when we plug values for petal width and sepal width into this simplified neural network. Since we have two inputs and one output, if we're going to draw a graph of what's going on, then we need a three-dimensional graph. The inputs, petal width and sepal width, each get the axis. And the output, the prediction for Setosa, is the y-axis. Note, to keep the math simple, I scaled the inputs to be between 0 for the smallest value and 1 for the largest value. So let's start at the corner, where petal and sepal width equals 0, and plug those values into the neural network. First, let's determine the x-axis coordinate for the top node in the hidden layer. We multiply the petal width by the weight associated with the connection to the top node in the hidden layer, -2.5, and we multiply the sepal width by the weight associated with its connection to the top node in the hidden layer, 0.6. Then we add the two terms together, and add the bias, 1.6, and that gives us the x-axis coordinate for the activation function, which is 1.6. Now we plug 1.6 into the ReLU activation function to get the y-axis coordinate, 1.6, because 1.6 is greater than 0. And 1.6 corresponds to this blue point on the graph when petal and sepal widths are both 0. Now let's increase petal width to 0.2, but keep sepal width at 0. Now, when we do the math, we get 1.1 for the x-axis coordinate and 1.1 for the y-axis coordinate. And 1.1 corresponds to this blue point on the graph. Likewise, when we increase petal width to the maximum value, 1, but keep sepal width at 0, we get these blue dots. Now let's increase sepal width to 0.2, and run values for petal width from 0 to 1 through the neural network. Likewise, if we keep increasing sepal width to 1 for different values of petal width, we get this blue bent surface. The bend corresponds to the points where the ReLU activation function set the y-axis values to 0. Now we multiply the y-axis value for each point by -0.1. For example, the original y-axis value for this point, when petal and sepal widths are both 0, is 1.6. And 1.6 times negative 0.1 equals negative 0.16, so the final point is here. Likewise, when we multiply all of the other y-axis coordinates by negative 0.1, we get this final blue bent surface. Now we do the exact same thing for the connections to the bottom node in the hidden layer. And we end up with this orange bent surface, where the bend occurs where the ReLU activation function set the y-axis values to 0. Then we multiply each y-axis coordinate by 1.5 to get the final orange bent surface. Now we add the y-axis coordinates on the blue bent surface to the y-axis coordinates on the orange bent surface. For example, the y-axis coordinate for this blue point is negative 0.16. And we add the y-axis coordinate for this orange point, 1.05, to get 0.89, the y-axis coordinate for this green point. Anyways, we do that for every single point, and ultimately, we end up with this green crinkled surface. Now, the last thing we do is add the final bias, 0, to each y-axis coordinate. And since adding 0 doesn't change the green crinkled surface, this is the output for setosa. Bam! Looking at the green crinkled surface, we see that the value for setosa is highest when the petal width is close to 0, and the value for setosa is lowest when the petal width is close to 1. Note, remember that we scale the inputs to be between 0 and 1, and thus, petal width equals 0 does not imply that the petal is 0 centimeters wide. Instead, 0 refers to the smallest width in the training dataset. Likewise, 1 means the largest width in the training dataset. Small bam. Now, to review the concept so far, when we have two inputs, the neural network creates curved or bent surfaces that are added together to make a new crinkled surface. That, in this case, we can use to make predictions about whether or not the species of an iris is setosa. For example, if we found this iris while walking in the woods, and the scaled petal width was 0.5, and the scaled sepal width was 0.37, then we can look at the y-axis value on the green crinkled surface that corresponds to these measurements, and see that this particular iris is probably not setosa because the y-axis value is closer to 0 than 1. And this is confirmed when we run the numbers through the neural network, and get 0.09. Bam. Now that we have a green crinkled surface for setosa, let's determine the output for the second species, versicolor. Just like before, we'll start with the connections to the top node in the hidden layer. And because the weights and biases are the same as before, we start out with the same blue bent surface. However, because we will multiply the y-axis coordinates by 2.4, let's change the range of the y-axis from 0 to 2 to negative 6 to 6. Bam. Now, multiplying the y-axis coordinates by 2.4 gives us this final blue bent surface. Now we create the orange bent surface from the bottom node in the hidden layer, and multiply the y-axis coordinates on the orange bent surface by negative 5.2. Now we add the y-axis coordinates from the two bent surfaces together to create this red crinkled surface. Lastly, we add the final bias, 0, to the y-axis coordinates on the red crinkled surface, and that gives us the final surface for predicting if the iris species is versicolor. Now, I'll admit, it's hard to see what values for petal or sepal widths will give versicolor a high score on this red crinkled surface. But when we change the y-axis scale from negative 6 to 6 to negative 0.5 to 1, we see that when petal width is close to 0.4, we will get a high value for versicolor. Double bam! Now, just like we did for setosa and versicolor, let's determine the crinkled surface for virginica. Just like before, we start with the blue bent surface from the top node in the hidden layer. Add S1 is virginix. Triple bam! At long last, we have crinkled surfaces for setosa, versicolor, and virginica. Now we can plug in the petal and sepal widths from the iris we found, and run the numbers through the neural network, and predict that this iris is versicolor because that output value, 0, the output values are sent to either something called argmax, arg, or something called softmax before a final decision is made. And we'll talk about argmax and softmax in the next StatQuest. If you want to review statistics and machine learning offline, check out the StatQuest study guides at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. Arg, Max, Soft, Max, StatQuest. Hello, I'm John, and welcome to StatQuest. Today we're going to talk about neural networks part 5, argmax and softmax. Note, this StatQuest assumes that you already understand the main ideas behind neural networks, the main ideas behind backpropagation, and how neural networks work with multiple input and output nodes. If not, the quests. The links are in the description below. In the StatQuest on neural networks with multiple input,